Here we go. What we are doing today, what we're starting with, guys. We're starting. Yeah. Okay. Is light. Light and matter, but pretty much light. All right. And now, mind you, light is pretty much the first thing that existed in the universe, but we didn't really begin to understand it until Einstein comes along. Okay. And in Einstein's theories of relativity and his thought experiments in the magic year of 1908, which was an amazing year for discovery for him, Einstein establishes that the speed of light is the cosmic speed limit. Meaning nothing can go faster than the speed of light in a straight distance. Okay, the fastest something can travel is equal to the speed of light.
So what happens if somehow something went faster than the speed of light?
Okay, well, it's a
Aren't we talking about it?
sort of yes, but our best understanding right now is that would something going faster than the speed of light would be would be the equivalent to dropping something near the surface of the earth and having it go up. It doesn't happen. It's not part of our universe. It's just an impossibility for. It would be dividing by zero. It would be it's a mathematical impossibility for our understanding right now. And the speed limit was determined by two guys named Michelson and Morley. Okay, and these guys actually, well, they didn't. They found the speed of light, but what their experiment actually did was an accident. They discovered Morley, M-O-R, or actually L-E-Y is what I should. Michelson, M-I-C-H-E-L-S-O-N, and Morley, but that's. I'm just giving you some history here. It's not really important to know the names. What they did is. It used to be thought that because we knew light was a wave, and all of the waves that we've discovered right now, ocean waves and sound waves and all the waves that we've determined, that we've studied, needed a medium. They needed something to vibrate in order to pass through them. And so the sound that we have vibrates the air, and waves have a periodic motion to the water. Okay, what they found was that light doesn't need a medium. Okay, and back then they called it the luminiferous ether. Ooh. Okay, or in other words, it was this stuff that we couldn't measure. We didn't know what it was. We couldn't tell, but it was the stuff that vibrates the stuff that light vibrates in order for the waves to pass through. They discovered that it doesn't have to exist. Okay, that there is no luminiferous ether, and the experiment is really elegant, but it's a bit complicated, and it's not worth our describing here. The important thing is that it doesn't need a medium. And because it doesn't need a medium, the speed of light is the same everywhere. And it's given by this. It's given by C. Luminiferous ether. Luminiferous. Okay. Luminiferous ether. Okay, the variable we're going to use for the speed of light is c, and c for constant. It's called a constant, and it is essentially the it's the granddaddy constant of them all, because all of our relativistic equations, all the stuff that all of our speed measurements are really based on the speed of light. And this equals 2.998 times 10 to the 8th, yep, 10 to the 8th meters per second. It's really fast. Okay. But this is treated just like any other speed that we've dealt with waves. And we've talked about waves being v in the past. Okay? And the velocity of a wave is equal to what the product of what two things? Velocity equals, oh, you guys were crushing it last week. What are the two things that we can multiply to give us our speed? All right. Okay, it's our frequency and our wavelength. And I drew my lambda the wrong way. Okay, so it's our frequency and our wavelength. Well, C has the same things. C is equal to the frequency of light times its wavelength. Well, there's two things going on here. The frequency of light the frequency of our light is when we talk about, say, radio frequencies and the frequency of cosmic radiation and all these sort of stuff, those are the same things. Okay, so we have all of these. In fact, that's what this picture is up here to the right, is the entire electromagnetic spectrum. Okay, and that's where, I skipped a step there. So let me go back. So our light is our frequency and multiplied by our wavelength. Okay, we can sort of equate wavelength to color, except that this is what our color looks like. Our color is this portion right here. All right, it is that little strip of all of the frequencies and all of the wavelengths that we see for light. That little bit right there is what we can see with our eyes. Okay, but all of the other stuff, so the power and the power and telephone waves, yes, those are frequencies, and we can transmit. We can transmit electricity. We can transmit telephone lines via these waves. Okay, to radio waves. Okay, and this is as their frequency is increasing. Microwaves, infrared, ultraviolet, X-rays, gamma rays, and so on. And right about here is the 1 meter wavelength. Okay, so we have, in all of these, we take our wavelength times our frequency, they all multiply to give us our speed of light. Yeah? Okay, so just some examples. The light that we see our purple light is okay, so our low wavelength equals our, gotta remember here, purples. We're looking at, this is like 400 nanometers, or 4 times 10 to the negative 7th meters, is our wavelength for our purple light. And our red light is about 700 nanometers, or 7 times 10 to the negative 7th. meters. And then we have all of the versions in between. So we have, next to that we have orange. Okay, and then we have yellow, but I don't have a yellow pen. 400 nanometers, which is 400 billionths of a meter. And then we have our green, and then our blues, and then our purples. And you may have heard of these before. These are the Roy G. Biv colors. You might have seen this with an I in there. However, there is no I, and there's a funny story with this. There are only 6 colors. Do you guys take an art class? There's 6 colors, right? Your color wheel has 6 colors. There's no indigo in your color wheel, right? Isaac Newton Isaac Newton was actually the first person to show that white light, the light that we can see, has our whole spectrum. And when he saw the spectrum, there's a yellow, and I don't have a yellow pen to put a yellow there. And I'm tweaking on it because my OCD is kicking in. I need a yellow there. He was the first one to show that white light contains all of the color. Now, you guys have seen this before. You guys look at rainbows. You guys have seen that just rainbows appear out of nowhere. Well, that's actually raindrops splitting the white light from the sun and refracting it and showing all of the colors and all the colors of the rainbow. Well, he recognized that there were only 6 colors: red, orange, yellow, green, blue, and violet. But he didn't like the fact that there were only 6 colors because, and I'm not kidding you here, he didn't like that there were only 6 colors because 6 colors was too close to the mark of the beast. Okay, he was a very devout Christian scientist, and it was 6 is not an okay number. You don't want 6 things. No. So he invented a darker blue in between blue and purple and called it indigo and said, okay, oh look, there's 7. And because he was such a renowned scientist and he was truly he was recognized as a genius in that time, you believed Isaac Newton because he said so. And so there must be 7 colors. Okay, when there's really only 6. Red, orange, yellow, green, blue, and violet. And so, however, these colors make up just a very small portion of the magnetic spectrum. All of this, okay, is the actual spectrum. And so there's a frequency times wavelength here, all the way around to the frequency times wavelength over here. And all of them, when you multiply them, give you the speed of light. Okay, so that is your introductory light lecture, and we can get going on